we'll start here. Okay, related rates. Now, keep saying that. Actually, we're doing implicit differentiation today. All right, today is day 16, I'm pretty sure, in class. We're over that 1/6 mark. We are sure AAHL and I don't know another number for this. 13 maybe?
Oh, yes.
I don't know what this is. Let me see if I can find it really quickly.
See that house over there? Oh. Me and I am stacking cards. Card games are we trying to stuff. Me and I am stacking the
Alright, implicit is actually 14.
No.
I know, I blew it. 514. Implicit. Now, here is the trick to implicit. Here is how I think other teachers, maybe not other teachers, I think that teachers who are trying to teach this to you without making it as simple as possible. Remember when we did like chain rule for the first time, and it was like, well, how come we haven't been doing chain rule on all this other stuff? And the answer was, well, because the inside was, the derivative was just 1, so who cares? We kind of have been doing the chain rule, but the derivative is 1, so we don't really need to waste our brain power on that. Basically, implicit, it's the same thing. We've already been doing implicit differentiation. Implicit differentiation is almost like you learn the rules of derivatives that you've been following, but you didn't even really know that it was a rule worth following, okay? So, let's think about if we go back and we just think about those optimization questions that we just did. Okay, so let's say that we had A equals X, Y. Okay. When we first did our optimization, we were looking at that box that we cut those corners out of, and we were kind of looking at something like this. And can we take the derivative of this? And the reality was, we didn't really know how to, because this has 3 variables. And if we start by saying that we're going to take the derivative of the area with respect to x, we haven't really included the y. And so then, once it's time for us to take the derivative of the y, what happens to the y? Does it just kind of disappear? And we've run into this issue of, we basically have too many variables. Okay, we have too much going on, so we figure out, the way optimization works is we figure out what a is, and then we only have 2 variables. And then when we take the derivative, we're able to just do our normal derivatives and everything works out great. Now, I guess this isn't a whole lot written on here, so I guess if you're taking notes, maybe too many variables. Okay. Up next, what if we see an equation where we've got y times x plus y plus x equals 5. Can we take the derivative of this? Well, now we've only got 2 variables, which is better. But they're just a mess and they're all jumbled up. We like taking derivatives by getting one thing on one side of the equal side and everything else on the other. And then we do that dy dx, dA dx, dp dx, whatever it is. For this question, can we get one of those variables all to one side and everything else on the other?
Yes.
I heard some no's and some yeses.
Wait, yeah, because if we push a y to the other side, we can take an x out as a GCF, and then we can move y plus 1 to the other side. Yeah, we can.
Right. I think yes, we can. Now, our traditional way to do this is to actually get y by itself.
Okay.
You could say what you saw for x, which would be fine, but we just like traditionally, let's do the y. So exactly, we could do this, right? We could move this x over here and make it minus x on that side. Then we could do a GCF, x plus 1 equals 5 minus x. We could divide this. And now we could take a derivative, and we would require quotient rule, but we could. So this is doable. And importantly, once we do the derivative, we will get dy dx. Now, I don't think we really need to do it. That's quotient rule practice, we don't really need that. Now, let me get some more room so that we can look at the monster problem we're about to look at. All right, so let's look at xy plus x squared y squared equals e to the x minus e to the y plus 2. All right, now, do we have too many variables here?
No. Or even
No, we have x's, y's, and e's, but e's not a variable, e's a constant. So, okay, we only have 2 letters, but we got a lot of x's and a lot of y's. Can we, siphon all of those y's to one side and have all the x's on the other, and so then we take a nice, beautiful derivative? The reality is, no way, right? I mean, even if the question was just this, it would probably be pretty tough. But with those e's, there's just no way. There's just no way. So, bottom line is, this is not going to be pretty. Right? We need to give up on y equals bleh. There's just no way that's going to happen. But the reality is, we can still do the derivative of this because it's got 2 letters. That's it. We can take the derivative. So implicit differentiation is basically just you are allowed to do the derivative even if you cannot isolate one of the variables. And the trick is you're gonna do exactly what you've always done. There's absolutely no new trick whatsoever. But the old trick that you've been doing, you didn't even really realize was a trick, okay? So here is implicit differentiation, okay? We'll leave a little gap and then we'll come back to the actual question. The way implicit differentiation works is that dy dx, which is what we've been doing, is created any time you derive y. Now, that is implicit differentiation. That's the whole thing. That's all we really need to learn today. That dy dx is created anytime you derive y, which is already a trick that we have been doing. If we go back to this, when we went to take the derivative, what did y turn into? Dy dx, right? It's the same thing. If you take the derivative of the y, it creates a dy dx. So actually what's happening here is that y, which is 1y, if you do the power rule on this, like imagine it's 1x. What's the derivative of 1x?
1.
Just 1. So what's the derivative of 1y? Just 1. But anytime you take the derivative of y, it creates a dy dx. It's like this radioactive junk that just kind of sprouts, okay? So that's what's been secretly happening for all of your questions so far, is you've been taking the derivative of y, which does not just magically become dy dx. It becomes 1, and then you have this growth of dy dx. So when we go to do this, let me take our mutant function here, clone it. Wow, that looked very nice. Let's take the derivative of this function. Okay, even though it's not pretty right now, just do the derivative. You need to do derivatives of x's when you need to, and derivatives of y's when you need to. And if you ever take a derivative of y, it just grows, it just sprouts out of nowhere, dy dx. Which means as we do the derivative of this, we're gonna get quite a few that are just gonna pop up in the middle of the question. So, let's start here. X, y. These are both variables. It's two things multiplied together. It's a product rule. So, what is the derivative? Let's do the derivative of the first one. The derivative of the first, which would be 1 times y. So this would start off with just a y. Plus, leave the first alone. Take the derivative of the second. What is the derivative of y? 1. And then dy dx, which has happened in the middle of the problem now, but it's not really any different from what's happened before. Again, what this is this is product rule. This is 1, the derivative of x, times leave it alone, times the derivative of y. So, nothing new here. It's just weird that this happened in the middle. Now this is the same thing, product rule, with a little bit more going on to it. So again, derivative of the first, 2x, leave the y alone. So do not put a dy dx on that, because we did not take the derivative of y. The second part of the product rule, who's got the second part of what the product rule will be?
I got it.
What do you got?
I have, well, you can put a 2 out front already.
Yeah, I like that.
And we have x squared, and it's y dy dx.
Yep.
Yeah.
Very impressive. I heard him say math god, and that's going too far, but he did do a good job. He did do a good job, and it's really like, don't overcomplicate it for yourself. Just do the derivatives of these variables, and then anytime that you do the derivative of a y, boom, a radioactive dy dx shows up, and you do that. What's the derivative of e to the x? E to the x. What's the derivative of negative e to the y? Well, if it was negative e to the x, it would be negative e to the x. But we're still doing the derivative of the top. It just happens to be 1, which is why we don't really care about it. So when we do e to the y, we're still doing the derivative of the y, which means it would be e to the y dy dx. And that dy dx, worth mentioning, is not in the exponents, it's just a normal number. Well, it's not really a normal number, but it's just a normal thing that's being multiplied by e to the y. And what's the derivative of 2? 0. Now I'll be honest, that is a sneakily, annoyingly common mistake to forget that your derivative of a constant is 0, because you're so locked in on the variables. I've made that mistake. I've seen other students make that mistake plenty of times. So, especially when you're doing the constants, like, just be aware that it's a mistake. So now, here's what we got. A dy dx, a dy dx, a dy dx. Normally the way this works is we have all the y's on one side, and then when we take the derivative, the dy dx is there already in a nice place for us. The way this is going to work is that, well, now the dy dx's are all throughout. Now we get to play like a little collector game of, instead of, remember this, solving for the y and moving things like Alec was recommending, math god. Well, here we are, same exact process, except for go out and collect all of these dy dx's, which again is not a difficult step. It's a messy step, but it's not, there's no difficulty in calculus here. This is all just algebra. Bring all your dy dx's over to one side. So I'm looking at this one, which can stay on the left, x dy dx, and all, let's do blue so I can figure out. So this person can stay, this person could stay, plus 2x squared y dy dx. This person needs to jump to the other side, so that negative e to the y dy dx would have to come over here and be positive e to the y dy dx. This piece over here can stay on the right side, e to the x. This piece can go over there, negative y. This piece can go over there, negative 2xy squared. And now we've got all of these on one side. We're going to do a GCF of all of these and move the rest of the junk. Now, after you do a couple of these questions, you might be able to do this step, one step, but just to kind of go through the motions on our very first question. dy dx has been GCF'd, leaving behind an x, leaving behind 2x squared y, leaving behind an e to the y, equals e to the x minus y minus 2x squared. And then just like when you do a normal, just divide all that junk to the other side. And so, dy dx is equal to a massive fraction. And that is implicit differentiation, all right? Again, kind of gross. But difficulty-wise, you just have to be patient. You got a whole lot of stuff. You have to be very, did I take the derivative of the y or not? If you do, you sprout that dy dx and then go clean it up. Now, here's what has happened, okay? Sure, we got our dy dx here, but the y's have persisted through derivation, through the derivative, right? Typically, we take a derivative and there's only one y which gets wiped out and there's no y's left. So because we've come up with this and it still has y's surviving, that means the slope is not only determined by the x value, it is also determined by the y value, which basically means what you're looking at here is not a polynomial. It is not a function. It is not a, vertical line test passing thing. This is gonna have double backs on itself, maybe triple backs on itself. This might be a circle or an oval or some sort of cardioid thing that has like a loop-de-loop in there. Because it has those y values, that means if they say, what is the tangent line at x equals 1, it might be two places, right? So that's all kind of coming when we start working with these implicit differentiations. You have a y value there and a y value there, giving you kind of two different things. So a little bit different than normal. Implicit differentiation. Okay. Here is
dismiss elements.
I don't think so, no. Which, I'm no expert and I still need to go looking through the curriculum a bit, but from what I understand, this is an HL only topic. And again, don't let yourself be mega scared of this because it is basically the same thing. It's just getting a lot messier. Now, the very first question on your worksheet that you're looking at, I was so nice to you is the exact same ugly graph expression that we worked with before. So obviously part A says confirm that P11 is on the curve. That would mean you need to plug in 1, 1 to the x's and the y's and make sure that you get a statement that is true. Part B, it says find dy dx. Well, that part we already did. So for part B, a lot of your time can be saved there. You guys try to get a head start on this, working on that, and I'm gonna pull up this on the board so we can do a couple questions together.
Just E. It just cancels out. E minus E. Can I just write the answer for B?
Yeah, just do that. I literally just did that.
That's enough by that.
Yeah, you can just write down an answer.
Alright.
There's 2 parts to it.
There's 2 parts actually.
Yeah, but for the part that's the one part.
You just plug in 1 for the derivative, right?
You plug 1 for x over.
E to 1 times minus 2 1 1 plus 2
Alright, we are pretty thickly in the weeds of calculus. How we feeling? Starting to get a little too crazy, or still got a grasp of it?
I think it's light work.
Just wait when we get into the math 50-part questions where you do all of these as well.
Alright. We're here. A says confirm 1, 1 is in the line, so that would use 1 times 1 plus 1 squared. 1 squared equals e to the 1 minus e to the 1 plus 2. That would be 1 plus 1, which is 2. E minus e is 0. 2 equals 2. That's good enough for part A. We've proven it. B, dy dx. Again, we already did that in the warm up. Me trying to save you some time. So normally you have to do all this work, but we did already. It was e to the x minus y. It will, spoiler. Minus 2xy squared. X plus 2x squared y.
Something wrong.
Oh, I think I wrote that wrong.
Or B part 2.
What am I missing? Should be plus.
Isn't it E minus
And I can just do it like that. Because I'm gonna say I cannot use that right there.
And then it says at point P, which means for part 2, we want to plug in 1, 1. Pretty nice plugging in of whoa.
Fedont. Come on.
So I got E minus 3 over E plus 3.
Yeah, that's valid.
Okay, well, that's a nice little answer. It's not too bad.
For real.
Find the equation of the tangent. Okay, this is also easy. C, I guess tangent will come when you were in algebra 1, you'd ever think you'd see a slope like that, you know what I'm saying? E minus 3 over E plus 3. That's just your rise over run, you know? It's just as simple as that. Normal, also pretty easy. Y minus 1 equals, flip it upside down, make it negative. E plus 3, E minus 3, First question, not too bad.
Valid.
Alright, here's what I gotta say on these questions. Question 3 is a behemoth.
3?
Question 3.
We're just not gonna do question 3. I gotta be honest. I started with question number 3 and I was like, I honestly have no idea how to proceed, and I looked up the key and I was like, I still don't really know what's going on. So honestly, number 3, whatever. Hopefully what we'll do is next time I see you on Tuesday,
Deviate number 3.
I'll figure that out, and maybe I'll explain that it's not a behemoth and I was just confused, but for now, I don't need you guys working on number 3 as long as I work on number 3.
Late breakthrough, man.
So number 2 is not quite as hard as it looks, but I do want to go through at least one piece of B. So what I'm gonna do, very cool, is I'm gonna give you guys maybe 2 minutes to find part A,
Valid.
because you guys need some time working on actually taking implicit differentiation. And what's nice about this is they've already even given you the answer, so you really know if you're right or wrong. Alright, 2 minutes. Were we able to get it?
I just had some sign issues.
Yes, so I also had some sign issues, but I noticed that everything was opposite. So if every sign is opposite, you can multiply by -1, which is multiplying by 1, so it's not really changing anything, but it will change all the signs on the top and all the signs on the bottom. So
Okay.
once I did that, it looked nice. Okay, so let's do one of these. I, and I. It says find the corners of the points where the tangent lines are parallel to, importantly, the points, like we talked about, this is a oval, and so where tangent, if I just draw a random tangent line like that, let's just say it's like 1/2 or something, there's another one down here which has the same one. So we kind of have double tangent balance. So we're going to be setting our derivative, which is a mess, but we've sorted it out, equal to whatever it needs to be equal to. If we want our tangent line to be parallel, that means same, to the line y equals x, this would be m equals 1, because y equals x has a slope of 1. The x-axis, what's the slope of the x-axis? 0. And the y-axis is undefined. So that's basically, we're gonna have to do 3 little trials of this equals blank and this equals. Maybe I'll do it like this. So for the first one, it needs to be equal to 1. 1 equals 2x minus y over x minus 2y. And multiply that to the other side. X minus 2y equals 2x minus y. Maybe get negative x equals positive y. What you guys got?
Yeah.
So that means whatever x is, whatever y is, they have the same number but opposite signs. So if it's 3, it would be negative 3. If it's 2, it would be negative 2. But that is not really a concrete answer, right? That's how x and y interact with each other, but you know, I don't know, does it make sense that as long as x and y were opposite numbers, you know, I don't know. The problem is numbers like 2 and negative 2 don't lie on our graph, so that can't be an answer. Numbers like 3 and negative 3 don't lie on our graph, or 1/2, negative 1/2 don't lie on our graph. So basically, we know that our points are along this line, but we need to figure out where does our oval actually have points on that line. Now, thinking about it that way is making it more complicated than it needs to be. Basically, we have this, negative x equals y, and we can just take that, plug it into the original, and then just figure out what the answer is. So we're just gonna do just like optimization, do substitution, we're gonna do the same thing for this, plug it in and see what we get. So basically, anytime I see a y, I'm gonna put a negative x. So that would be x squared minus x y, negative x, plus negative x squared equals 3. So that's the original, swapping out the y's for negative x's. That's gonna be x squared plus x squared plus x squared equals 3, which is probably one of the strangest results of substitution you've seen in your math career, maybe. But that's gonna be 3x squared equals 3, divide by 3, x squared equals 1, square root both sides, x equals positive or negative 1. Now, this is not just 2 possible answers and the negative doesn't make sense, which is what we're doing for optimization. This is 2 possible answers and both of these are answers. So now, our 2 answers are positive 1, comma, and negative 1, comma. Remember, the x and the y, negative x equals y. So here we would have negative 1, here we would have positive 1. And those are the two places. Now, looking at the graph, honestly, we probably could have just reasoned out visually that that was the case. Where are we parallel to y equals x? Well, it looks like it's somewhere around here. And if you had to guess where it was, you probably would have guessed 1, -1, and -1, +1. The other two questions are asking you about where it's equal to 0 and where it is undefined, which again, you probably could visually reason out, but mathematically, you need to do the implicit. Look at this paper before we turn it off. I can stop the video, but again, we talked about number 3. We're definitely not doing that. Number 4 starts off some short style questions. They get pretty quick. Number 5 is pretty quick. Then we got 2 more, 6, 7. Yeah, I guess just don't do number 3. Should be good.